So on Monday, we discussed about how we use the current mode control to control the brushless DC motor. And so typical current mode control, like this diagram. So we try to use this mode transistor to energize them in certain mode operation. So each conduction we're going to connect with two windings. So for instance, we got three-phase winding, two windings we connected. Then you can see that each one of them will have two resistors for the winding resistor and two inductor and two band in EMF. They all adding together and then try to become a load or the resistance to the incoming voltage. So that's why when you turn on two devices, you can see the current go up here. But however, when you turn off this one, then the dial will be conducting and then current will be decreasing. So you can see that the slope here will be decreasing. That's the current, the IDT of the current. So, and then from this, then we know that when the current increasing and decreasing, the ripple should be the same. Because otherwise the current will keep increasing indefinitely or decrease indefinitely. So that's why if we put these two equations together, then we are able to work out the average current. So now then for these two, we're putting them together, then add. So this is rising, this decreasing, rising and decreasing should be the same. Then put them in the zero. So turn on time will be dTs, and turn off duration will be 1 minus dTs. D is the duty ratio for the transistor. So that's why we can work out the average current will be equal to this one. That is to say, we can control the motor current by using a duty ratio D. So that's one of the typical way we control DC motor. We can able to use the duty ratio to control them. So that's one of the methods we have been using. So in this case, if we put them into a control diagram, that's what we're going to see. For example, we have brushless DC motor, then we use the shaft here, we're using tackle generator to measure the speed. So that will be negative feedback, and then we also have a set point for the speed reference, how much that speed will compare to our demand speed. And then the error signal here will go to the controller. So you haven't learned about the controller here, but the controller here mainly is to look after the error signal here. So this error, for instance, if the measured speed is lower than the speed reference, we'll try to increase the duty ratio to compensate, and vice versa. So eventually we can get to a state that we are able to have a stable speed. So in here, we also try to measure the current. So in the current loop here, that will be, we have also current demand or current reference to tell the system what kind of current we're trying to control it. The torque usually proportional to the current. So most of cases, we can just measure the current to use current to control the motor torque. So that basically our configuration. Of course, the detailed motor control will be more complicated, but in here we show you how the basic control loop look like. So in here we do have a speed loop to control the motor speed. So in here we'll control the inverter, what kind of the rotation we try to go for. So that means we can fire each one of the stator winding in sequential manner to control the speed. The motor will be so-called the synchronous motor. So we will follow the rotor position to fire the associated winding. And then to increase the torque, we need to inject high current or low current to control the motor torque. So that's basically all the mode that we use are two loops. One is the current loop, which is control the torque. Another loop will be control the motor speed, which will be just similar to that one. So now next thing to understand will be how are we going to control the speed. If you go back to the previous diagram, we can see that the motor speed actually, you can see the signal here, that is the period of the operation. So one period will be mean we're trying to find the pulses here so that we will follow the rotor rotation. So that is to see if you like to have a higher speed of rotation, so that frequency, we're going to have a higher speed in order to do that. Of course, every time we need to monitor the position of rotor, make sure that we won't higher speed or lower speed than the rotor. We need to make them synchronized. Yes.
So in the diagram, we had torque, with the speed controller and the torque controller. So if we change the reference to the current, wouldn't it also change?
Yes, that's a really good question. You can go back to this diagram and see that these two are related to each other. You can see that if, for instance, you try to speed control, and then you try to ask the motor to catch up with your final pulses, because the motor will go to any position, you need to find the associated winding. But usually that can be good, but however, you find that you cannot catch up over your motor torque is not sufficient to catch up. In this case, you need to increase the current reference, the high torque to do that, and also vice versa. So these two are correlated to each other. But if you are just separate the two for you so they understand, for normal motor control, you need to control the torque and also the speed. These two are correlated.
So we could change both of them then depending to make sure it syncs.
Yes, so that means these two is a very simple. There will be connection between them. So, but at the moment, we're learning about the control engineering, so at the moment, to show you how a motor control system looks like. So, and in here, I'm going to show you how we're going to control the current. Yeah, so there's a very simple diagram. I think what you learned before in the digital electronics, you learn about the SR flip-flop. Tell me, what's the operation for SR flip-flop?
I can't remember.
I'm not remembering. Isn't that set reset?
That's all. So what's the point for S? What's R? What's the Q?
Set, reset, and then
So,
You go first.
set. That's the set input, and then you have your reset input, and then you have Q your output.
Yeah. Okay. So basically, we have S to set it. Then we can have a fixed frequency clock to set it to turn on, and then the so that is to say these pulses we're going to inject into here. So forth. And then we have a current reference here. We also measure the current in the transistor. You see the transistor current here will also equal to the winding current because they're connected in series. So that we say I don't need to actually measure the winding current. I can put a sensor here to measure this transistor current. So when the transistor in turn on, the current will go up increasing. That is what we show in this triangle wave. So below the current length now on, the current will be increasing. And then when the current reaching the current reference, then we try to have a pulse here to reset it. When you reset, then in this case, the Q will go back to zero. So basically what we're trying to do would be, once we have pulses here, the S pulse, we have a fine pulse for, that is the so-called our switching frequency. And then our Q will therefore turn on here, try to become logic 1. And then when the current, so the current here will increase. Yeah, when the current reach the reference, so this will therefore trigger the reset, and then that's why we go back to, so now then this current will therefore stop here. So next time we will therefore incorporate. And the current will therefore decrease like that, and then next pulse will turn on again, and then we'll start to not very good. I need to withdraw it properly. Wait. Here or joy. Oh, you cannot clear. Why is that? Let me. Anyway, let me redraw it now. The current here, the current. We know the current is when we have the pulse, when it turn on. So this current should be increasing. When up to this point, when the current touching the reference, then the comparator will reset it, and then we'll set it. Once we set, then the transistor will be turned off. We're going back down here. So when next cycle, when the Q is turned on, this will therefore increasing. So that's the pulses. We'll make use of XR34 to control the transistor being turned on and turned off. I guess next page I have that. So that's what happens. So when we set the signal, the transistor being turned on, so the current will increase until you touching the reference current, and then the SR34 will turn off the transistor, then the current will therefore increase. And what we mentioned just now, when the transistor turn off, the current will go through the diode, the current will decrease. So we continue with this process, then that is to say, that is the maximum current for the transistor, or the maximum current for the winding. So you can see that in here, that's how it look like. So originally we want to examine how to control the average current, but now then we are using this current control, we set this I reference to like that. So that's how we're going to control the current. So this shows you a very simple way how we're able to control current by using so-called peak current mode control. So that is the peak current control. We are not setting up the average mode control, but we're using peak current control. You can see that this method is much simpler than before because we're just using a simple SR34. We're able to control the maximum current. And the second question will be, would there be a problem because we try to control this average current here, but not the peak current? Do you think that would be a problem? Or that will we can't control accurate current? What do you think?
I think it is an issue.
That's an issue. Depend on the ripple. Yeah.
Wait, you said, will there be an issue controlling the curve itself?
No, would that be an issue? We are only controlling the peak amount at this point, not the average curve. The motor, of course, we prefer average curve, not the peak curve. The motor only understand the average curve here, that's very difficult. So that's what we're trying to do. So for instance, I prefer the motor will control this average, but this only I peak current. So that means we are actually having less current than before. But however, firstly, this method is simple. We're using single logic controller can do that. Secondly, will be if we use really high frequency, this ripple can be really small. In here, I just do it so exaggerating. Probably this only about 1% of the current, maybe 0.1%. When we use really high frequency, then the IDT here will become really small, the DI will be small. You can see that the LDI dt equal to V equal to applied voltage. So we have the inductance here from the winding. This DI will be equal to this one, right? So dt will be equal to this period. So if our switching frequency, the frequency operation, we increase it. You can imagine if we use 1 kilohertz to drive them, we got this thing. But if we increase to 10 kilohertz, that means that the period here, 1 over Fs, will be only here. So that means the ripple can decrease to this amount, and then next time we'll start to again. So we can do this, right? So you can imagine powerful of the power electronic will be, we are able to use really high frequency to decrease ripple. If here you are, if for instance I use 10 kilohertz, 1 kilohertz, but I decrease to 10 kilohertz will be this ripple. The ripple can decrease by 10 times. So that is to say, you can imagine nowadays, the peak here, but only increase by a little bit, it doesn't make much difference. If you find that the top is not sufficient, you can increase a little bit of the top reference or current reference. to do the compensation. So that's one of the beauty. When we use high frequency operation, then we are able to do that. So when we use really high frequency, the ripple will much lower, then the IMFN will be very close to the motor current. So that, of course, in here, when you learn about the control engineering, we can show you the method how to control average current. But here will be, I give you a very simple diagram. Together with your SR fault knowledge, you can able to work out the peak current control. All right. Any question? Do you get that? Do you? I think you all learn SR fault. So this will be a very nice example how to correlate your digital electronic to the current mode control. Current mode control is quite really important for all the motor drive. As I mentioned before, most of the motor torque are proportional to the current. So how to measure the current? We can use sensor here, or sometimes we can put a resistor here using the voltage across the resistor to measure the current, like what we did in the lab. You can see that if I put a 1 ohm resistor here, 1 ohm multiplied by current equal to the voltage, so that will be exactly proportional to the current. You can fit that in here. For this comparator, actually, we don't inject the current there. We only inject the voltage. For comparator, this kind of IC, they only understand voltage. So for this one, I say, I want to control this current to say 1 amp. Then I use 1 ohm here that will represent 1 volt equal to 1 amp. So in the current reference here, I put in 1 volt in here. Then that would be equal to control this current to be 1 amp. So that is the logic we try to do. We don't inject any current in control electronic. You control all the measurement, like the current in the voltage, because all operators have the digital electronic, they only understand voltage. They don't have any current. So that's why this one or this, you convert all the measurement into the voltage to go to an SR3 processor. So that's how we show you how to work with the control electronics. Any question? Good. So talk about control electronics, then there's a number of the typical controller will be now available for the control of this kind of the brushless DC motor. Like this one, a controller B620 would be a really popular controller. Like what you're using in the DC bus motor for your computer. And then, of course, we don't have a really large controller like what we did in the lab, but we only have a really small chip here, only just like less than our pin. Then we can all the pins will located in here. Firstly, you can see that we have a 3 inverter. The inverter to drive them, so the inverter already embedded inside the IC here. So we have a 6 transistor, so this will connect to the 3 phases, the 3 winding. So this output, we can connect them to our wind connection of the motor winding. And then, as I mentioned, we need the positional sensor. So in here we got 4 event point sensor. You use to connect this one to the motor. The motor will have a connection for the position for each of the winding position. So your connect will be it. So they will match up with the requirement of the control voltage for each one of them. And then first time we say we are talking about the kernel control. We did error amplifying, which that also this one is already available in this controller chip. So that's to say, if you use this controller chip, you can actually implement this logic quite easily. And probably you can only need an external SR3 port, then you can control the power, control the speed using a single chip only as for this one. That's why I can see that most today, all the brushless DC motor, you don't need huge computer to do that. Only single chip, you can able to control everything. So finally, let's go to some tutorial problem to see if we're able to grab the concept. You see this kind of tutorial really similar to the DC motor. So you understand the DC motor, so this tutorial will be just straightforward. So now we have Brushless DC motor BLDC have this parameter, the phase resistance. Again, we use the phase resistance because that will be per phase per winding. And then the combined torque constant will be 0.05. And then the motor voltage, the input voltage, but bus voltage will be 50. The on-state voltage drop will be 1 volt again. So that means up 50 volt, we need to consider 2 voltage drop for 2 transistors. And then now the motor running at 400 radian per second, you need to achieve a current 5 to produce the torque. So that means that 5 relate 5 equal to the requirement of the torque. So now then calculate duty ratio, and then we also try to calculate efficiency of the motor, the driver, and the system efficiency. So to calculate efficiency of motor, usually relate to the motor winding resistance. Yeah, that's mainly contribute to the efficiency. And then, of course, the system efficiency also contributed by the motor resistance plus the on-state voltage. Any on-state voltage from the transistor will contribute to the power losses that will contribute to the total losses. So let's see how we're going to do that. So with the back EMF will be equal to the constant multiplied by omega. We have 400 here, 0.05, we got 20 volt. So because we have 2 winding here, we multiply by 2, become 40 volt. So the total voltage will be 40. You see the input voltage roughly about, say, 50 minus 2, 48 volt. You can imagine we are now having 48 volt applied to the motor with the back EMF of about 40. So that is to say you got 48 volt now. So now then we use that equation to calculate average current. So that now then we can just put in the V dash, and duty ratio is the one we're going to calculate. We calculate what kind of duty ratio is needed to reduce the voltage so they're able to match up with this back EMF of 40. So after we've done that equation, you can therefore calculate duty ratio equal to 0.93. Really large duty ratio. The next thing is calculate about the power. The power, we use the typical torque equation. So that's the same kind of torque equation, 0.05 multiplied by 5, 0.25, because we got 2 winding. Each winding contributes to 0.25 Newton meter. So that means in here we got 2 of them. So the total output power will be equal to 200. That's the mechanical output power. Next, we calculate input power, IDC 50. So that's the input voltage, not 48 volt, but 50. And multiply by average current 5 to 450. So typically then the ratio will give you the efficiency, which will give you about a number of efficiency we have here. Firstly, for the motor efficiency, we are now applying the 48 volt to the motor after the transistor voltage drop. So in here, the base value we use 48 volt here. So the motor efficiency will be 83. And the system efficiency, we use the input voltage from here, from the input power. Then we got 80. And the ratio of these two will give you the driver efficiency. The driver, that means they're including the transistor voltage drop here. So we got 96. So that is to say now that you can get all the 3 efficiency. So you can see that this tutorial is quite straightforward. We just basically to use the same equation we have for the DC motor, but now that we also consider a number of power losses, including the transistor, including the winding resistance. So this kind of example, quite straightforward without any complication. Any problem? Any questions? Simple one. So next thing is to see, now then we try to reduce the torque to 40%. Then assume that we know the current is also proportional to torque. When the torque reduced to 40%, our average current also reduced to 40%. So we use the same equation, and the current being reduced, then we calculate duty ratio. So now duty ratio need to drop to 0.87. You can see that we dropped the current so much down to 40%, but the duty ratio is not dropping 40%. Only dropped to about 0.8. Why is that?
Is it because the current only affected the time, like dropping about 40 only takes the time for when it's off? Like the.
Not only this. more than that.
40, because you did 40 times the line as well.
Close enough. Any second comment?
I guess not the total.
The thing is, most of the voltage on primary page will appear in the back EMF. Try to convert the back EMF. The back EMF like this problem, previous problem only 40 volt, the back EMF. So that is to say we only have the different in voltage and the back EMF is different, will be used to control the current. So that's why our big ratio in here you can see that we don't need to have a large change of big ratio. This big ratio actually quite proportional to the output voltage. So if we have fully turn on, big ratio equal to 1. If we half turn on transistor, then big ratio equal to 0.5. So big ratio actually proportional to output voltage to the motor, but we don't need to reduce the voltage to the motor up to half because most of voltage we need to supply to the back EMF. So that's why we need to, you can observe that the duty ratio only changes slightly because most of voltage still appear in here. The input voltage is still 48 and the back EMF is still 40. We only have a little bit of the control ability in the duty ratio to vary the voltage drop on the winding resistor. So that's why you can see that duty ratio only changes slightly. So you can see that the system are really sensitive. If you want to change the motor torque, the duty ratio will only adjust slightly, rather than a big amount of the variation. So now then the output power, of course we got 2 windings, so again we got output power will be 80. So now then we do everything again about the efficiency. So the input power again is system input power 50 multiplied by current, the current reduced to 40%, we got 100 watt of power. So the motor efficiency, we are using 48 volt because that's the voltage applied to the motor. So we got efficiency is 83. The system efficiency will be these two ratio will be 80%. And the driver efficiency, we are using these two ratio to calculate that. Then we 96%. So that's why I can see that if compared to previous one, 83, 80, 96. So it seems the efficiency, right, has not been changed that much. Right? Mainly in here, because why there's no change? Because the motor efficiency, we only change the input voltage. The input voltage unchanged, we only change the current. And the current only try to appear in the voltage drop on the winding resistor. And that's the motor itself, the efficiency. You can see that the motor efficiency 83, before also 83. The driver efficiency is 96, now also 96. Because we have constant voltage drop in the transistor, 1 volt for each transistor. So we have the current pass through that. So when we change the current, the voltage drop in the transistor also change accordingly. So we don't have any I-square relationship there. If something is I-square relationship, the efficiency will change in non-linear manner. But now they can see that the voltage drop of the power losses in the driver are proportional to the voltage drop of the transistor. But anyway, what we can observe here, for this kind of linear control, we do not observe any change. So another more importantly for DC brushless motor will be about the ripple. Just now we mentioned, you can see the current on triangular shape. We will worry about what kind of ripple it may be there. So in here, we examine about the ripple. How do we calculate the ripple? So firstly, we got the torque equation like that. Torque equal to a torque constant multiplied by the current. That's the typical equation. It's the same. So now then, if the current IAFA plus a ripple there, if we know there's a higher, when the current increased from one level to the other level, then you can see that the torque will be increased by this ripple. So the difference between these two equations must equal to ripple torque. Ripple torque, that means we have constant torque here, produce a certain acceleration. But when the torque ripple increase, then we may appear some vibration. So this kind of top ripple will cause the mode rotation become also have a ripple rotation, which we don't quite want that to happen. So that means now then the torque ripple, we can simplify it, the torque constant multiplied by the current ripple. So now then, we know for all the power electronic driver, the current is not straight line, it's not a constant DC with the ripple. So anything appear in this current ripple will therefore appear in the torque ripple. So that is to say, when we consider this kind of the current, so this ripple will therefore appear as torque ripple. We like to see how much torque ripple it is. Will that be a problem? As I mentioned before, the ripple can be controllable. We can use higher frequency to control it. 10 kHz is a typical. You can also use 20 kHz, maybe 50 kHz, depend on our control electronic to do that. But tens of kilohertz is quite common. So you actually reduce the ripple a big amount. So we usually don't worry too much about the ripple. But anyways, like to see how the ripple look like. So again, we use the previous tutorial. We calculate them to see what kind of ripple we are talking about. So now then you can see that again, 50 volt here. To calculate the ripple, we need to know the inductance because LDIDT, that will inductance. So assume the inductance will be equal to millihenry. The torque constant is unchanged. We're now using 20 kHz to see, and then we calculate delta I and delta T. So you can see that now the total inductance, again, because we got two phases, adding together will be 4 millihenry. The period, we are now using 20K, so that means the period equal to 50 milliseconds. So now then we use our ripple equation, that's a typical ripple equation we use. We just put all the parameters here. So 50 volt minus 2 volt from the transistor voltage drop become the actual voltage applied to the motor. Back EMF 40, average current 2, and then resistance will equal to 1. That's a combination of 2 resistors, 0.5, right? And after that, we can get the top ripple current become 65. So we put this into here. We can work out top ripple 3.28 million Newton meter. So obviously that's a really small. We usually talk about the Newton meter will be quite a few Newton meter, 10 Newton meter, 20 Newton meter. So this is really small. So we compare that with our output torque will be only 3.2%. So that's a really much reasonable. We usually assume the motor ripple torque will be less than 5%. Then if your control system needs to be really dedicated, you can use a high frequency to do that. For instance, you're now controlling the robot arm, only 3% of the additional movement, probably won't feel anything. But if you like to have a more sophisticated control, then you can increase your shifting frequency. We are now using 15 milliseconds. You can increase the frequency, then you can decrease the T. All right. So this question is also quite straightforward to show you about when we use current control, we got the current ripple. Current ripple, we got the ripple torque. Then in here, this sample shows you what kind of ripple torque we're talking about. How can we improve that? Maybe in exam I ask you now got 3.4%. How are you going to reduce by half without any changing the motor? It's the same type of the motor, same type of the driver. Now you have 3.2. Can you reduce by half? What are you going to do?
Wouldn't you decrease the frequency since period is 1/n?
Double the frequency. When you double the frequency, then you're decreasing the peak and period TS, you reduce it by half. Then your ripple will automatically reduce by half. So we increase the frequency. So we don't need to do anything. We just increase the shifting frequency or the peak and frequency. That's it. The motor is the same, control is the same. You just change the clock pulses here. Just change double the frequency here. The ripple will reduce by half. Then the next question you may ask me, oh, why don't we use really high, 100K, 200K, 1 megahertz? Of course, that will need by all these components. Then they do have a limitation, they can't do indefinitely. So that's why. But today, 10K, 20K, 50 kilohertz is quite straightforward. All the IC can do that. But we do have some limitation like the transistor. High frequency transistor will be more expensive. Popular, you can use the Y10K one. Maybe silicon carbide, you can use much higher frequency. But when the transistor at high frequency, usually the firstly more expensive. Secondly, will be the power rate current can be too high. We cannot have transistor for really high power and high frequency. So they have a trade-off. So that means for really high power like the train, aircraft, they are high power talking about megawatt. Their switching frequency cannot be too high, cannot be 1 megahertz, usually about 50 kilohertz. For train, we talk about several megahertz, megawatts power. Megawatt properly, we have to use transistor only 20 kilohertz as a maximum. So they do have correlation. So in next academic year, when you go for my power electronic courses, then you know more about the device level, how to select a good component power device. Anyway, so that finishes off our brushless DC motor. So to conclude what we have learned, you can see that we're now using show you the switching pulse pattern for the brushless DC motor. So this is one of the typical way we control that. I also show you how to use the simple current control that give you a start of how to control a DC motor, or including a brushless DC motor or DC motor, how to use current control. The current control is one way we can able to control motor torque. And the current control here, we just using the top transistor, bottom transistor to turn on and turn off in order to fulfill the current control. You can see the method are really straightforward. So this kind of switching, in the future, you will learn something about the buck converter. Have you learned anything about the buck converter? Yeah, you should learn that if you go for the power electronic course or the electronic tools, then you will learn the buck converter. So in next semester, we have electronic tool. I'm not quite sure anyone go for my electronic tool. Then we will also show you the buck converter. So that will be how we're going to control many electronic or power conversion. And you can see that our efficiency calculation show that even though we change the torque, it doesn't affect the overall efficiency. Because you can see that the calculations here are mainly linear proportional. So that means when we use certain power level, the efficiency will fix it. Even though we change the output torque, change the current, we does not change the efficiency. This is a nice thing to hear that. Another important conclusion will be the ripple torque. We can use high frequency to control ripple. So in this case, nice thing to have. We only invest high frequency power devices like the transistor, digital low object, then able to reduce the torque. So that's all for the brushless DC, and 2 lectures to show you how we further on to change the DC motor into the brushless DC motor. Any question? And the tutorial also quite simple, very similar to DC motor. So, and then after that, the next more important topic we go for will be really important motor, switch reluctance motor. So let's end here and then go for the next one.